welcome to today's lesson on lenses and how they refract light. Today, our main objective is to describe the two different types of lenses, double convex and concave lenses. And we'll talk about what types of images they form, a couple of properties about them in terms of whether they diverge or converge light. So we'll talk about what those terms mean as we go along. And then we'll mention as we go through the lesson today as well, some technologies that are involved that use lenses that I'm sure we've already talked about in class or you've heard about before, namely microscopes, eyeglasses, telescopes, binoculars, those types of things. Okay, so as we go along to our first slide today, just make note that a lens is a piece of curved glass or other transparent material, but it's got to be smooth and regularly shaped. If it has imperfections in it, then it won't focus light in predictable ways. And so that is the key. They're smooth and regular shaped so that light is refracted in a very predictable way, such that we can focus the light onto a very specific spot. So for example, our corrective lenses help us to focus light so that it hits the back of our eye at the retina. Binoculars are designed so that they're much like corrective lenses, except that they have a magnifying power as well. And same thing with microscopes and telescopes. The light needs to be focused very specifically so that ultimately it lands on the back of our retina and causes the desired magnification effect. Okay, so in saying that, there are two basic types of lenses. The first lens we're going to talk about today is called the concave lens. And the concave lens is got this very distinct shape. It looks like it's kind of curved inwards, maybe is the best way to talk about it there. Typically, we'll describe it as being thinner in the center and thicker at the edges. Okay, and I always like to think of the word cave. So we're kind of like light is entering a cave, and that helps me remember the shape of a concave lens. Okay, and as you can see in this diagram here, light hits the lens, and these are all parallel, right? So let's just imagine they're coming from a distant object, the light's all coming in parallel, and it hits the lens, and in this case, a concave lens, you can see that the refraction of light is causing the light rays on the opposite side of the lens to spread out. And this is called divergence, okay? The light is diverging. Another thing you should pick up from the last lesson here is that light rays that come and hit the center of a lens, you don't see any refraction, and that's because the incident angle is equal to the refracted angle, which are both 0 degrees. So remember, if you drew your normal that is perpendicular to the surface of the lens here, that it hits the lens at a 0 degree incidence, and therefore the refracted angle is also 0 degrees. When you hit the lens at other angles other than 0 degrees, so if you could imagine there is a normal line sticking out there, because there's a different, at a 0 degree angle, it won't refract, but any angle other than 0 degrees, you will get refraction. And so that's why at the center of a lens, there's no refraction, but as you move to the edges, you will see the refraction becoming more and more apparent. This light ray is bent more than this light ray, and of course this one, no bend in the light ray at all. Okay, and so you can see here that the light rays are diverging. So you would think, well, if the light rays are diverging, why would this be useful? Okay, and when we talk later in today's lesson about eyeglasses, you'll see that a condition called nearsightedness and a condition called farsightedness. And I believe it is people that see nearsighted. I may get this wrong, so you know what? I'll just leave it till we get to that slide, but I'm pretty sure nearsighted people require the use of concave lenses to help them see better. But yeah, I forget these things every once in a while as well. So we'll review it when we get to it here. But that will be a key learning point. We'll want to make sure that we understand uh, what kind of lens is used to correct what kind of vision problem. Okay, moving on, we're going to switch to convex lenses. So I show you an example here of a convex lens, this magnifying glass. And typically, convex lenses cause what we call a convergence of light. And so we'll look at that here on the next slide. So a key characteristic here is that it bulges at the center, so it's very thick, and then it tapers off to a point at either extreme. And remember, this is a three-dimensional object, so this is it's got a circular shape to it. Think of an eyeglass lens, and this white spot in the middle here would actually be representative of the edge that's coming towards us. But just remember, it's got a curvature all the way throughout the lens. Here's a video that you'll see again in a little bit, and that video will show you exactly what I'm trying to talk to you about. Notice again that as the light rays hit the lens, um, in the center here, there is no refraction, and it just goes straight forward. But when we look at the extremes, it hits the lens. This time, instead of causing the light to diverge, it's actually causing the light to converge. And so, depending on what side you're coming from, it will bend down or up in this diagram. And of course, you can see all the other variations as we go through, but no matter what, they will all converge at this focal point as long as we have very particularly and accurately, precisely made lens, so that all those rays will converge to a focal point. If you had a lens that had any aberrations in it, typically they don't form clear images because of those imperfections. Okay, and in this case, I just mentioned it earlier, all these light rays converge. So this is a converging lens, and they will form images that are real. And typically, in most of the uh, lenses that we talk about in technology, like microscopes, telescopes, binoculars, we are talking about convex lenses. The reason we'll talk about concave lenses today is because that will help correct vision problems for individuals that have misshaped lenses naturally. And sometimes you got farsightedness, and sometimes you have nearsightedness. And depending on the situation, you'll need your what's it called there? The optometrist will, when they measure your eye and find out what the aberrations are in your eye, they know what proper lens that you will need to correct your vision problem. All right. So I guess another thing I should mention here is that this focal point also changes based on the the curvature of the lens. So if you have lenses that are more curvy, you'll have focal points that are closer and closer to the lens. And when they're elongated like this one, you can get the focal point to be further and further away. And this, of course, would need to be designed specifically to the technology that it's being used in terms of how it's laid out, how close this lens is to another lens, and so on. All right. So there's a couple main reasons that we like to use convex lenses. There's, I guess, two main reasons that they're very useful. And one is that they act very well as light collectors because they're converging light. So you see here we got an image of a refracting telescope. And as the light comes through the as the light comes through the objective lens, it is bending and refracting the light to form an image on the second lens that will eventually end up as an image on your eye. And this collecting of light is what allows us to see starlight that is very, very infinitesimally dim, if you will. There's not a lot of it there, but because it collects it, we can use that collected light to see an image. So that's one of the reasons we can see planets that are far away. When we talk about the Hubble Space Telescope, it can see images of very, very distant stars and galaxies because it's got such a massive lens that it can actually see and collect a lot of light, considering that the little amount that actually hits our proximity in the universe. All right. Another technology, I guess, wouldn't be a bad idea to talk about here was microscopes. They'll also need to collect a lot of light, the lens in a microscope, because the objects that we are viewing are so tiny, they don't have very much light passing through them or being reflected off of them. And so that little minuscule amount of light needs to be collected. And again, that's why we need to use convex lenses in microscopes. Okay, and then the second, this is a really important reason, is that because they converge light, they form real images. Okay, when we remember we talked about mirrors the other day, and in the convex mirrors do not form real images, they form virtual images, images that were upside down, or sorry, right side up, but they were formed on the opposite side of the mirror. They don't appear to us. We can't see that image on a screen or something like that. Whereas sorry, a convex lens will actually converge light to a focus point, and it will allow us to project an image onto a screen. And if you think about your projectors in classrooms, it is convex lenses that are allowing that image to be shot out of the machine onto either the whiteboard or the screen that's mounted through the room. All right, here talking about hyperopia here as well. This here is an example of farsightedness, and we'll talk more about this in a little bit here, so I won't talk about it now. But if you can imagine these two lines converging, they'd converge about out here. And when the light rays converge behind this little area, special area here, it's called the retina. When they converge behind the retina, this is what we call farsightedness. Hyperopia is the little bit more scientific name for it here. And you can see with a convex lens here causes the light to bend faster. Okay, so it causes a bending out here of the light before it even hits your eyeball. And it will now focus properly on the retina. Okay, so that's a convex. And so that is with farsightedness. With nearsightedness, quite often the focal point is in front of the retina. And so you can imagine you're going to use a different kind of lens, the concave lens, to cause the light to diverge a little bit so that instead of focusing up here, it would focus back here. All right. I'm not going to watch this video with you guys, but it's a great explanation about convex and concave lenses. So you guys, I'll ask you to spend 5 minutes of your time to watch this today. Again, this is here more for your notes. You're going to do an activity in either tomorrow or the day after where I'm going to ask that you identify the type, the qualities, describe the image that's formed. So if you take a look here, this is the focal point for the lens. What they don't show on here is that the 2F, or the center point for the lens, would be out here. So in this case, the object is between the center and the focal, or the 2F and the focal. And you'll notice here, using our rays, that it forms an image that is on the opposite side of the lens, which makes sense in a lens here. It is inverted. It is larger than the original object, and it is a real image. Notice that the lines that are the rays that are connecting to this image here are all solid lines, which is indicating that it is a real image form. Here, this is the focal, so the center point, or the 2F point, would be about here. So this is where the object is outside of both the center and the focal point. And you can see here that the image is again inverted. Again, it's real, but in this case, it is smaller. All right. again, just looking at different images here. So again, focal point, your center point would be out here. So again, you can see that the image is inverted, it's smaller, and it's a real image. Again, another image here showing similar, the center point would be here. It's between the center, the object is between the center point and the focal point. And again, you can see the image produced is inverted, larger, and it is a real image. Okay. And then in this case here, when the object is inside the focal point, you can actually see here that the light rays will start diverging. And in fact, what they form is a virtual image. So this bigger guy here is the virtual image. And you won't be actually able to see this image. It's virtual. It is a larger image and it is upright. And if you remember, real images will always be inverted or upside down. They can be larger or smaller, but they'll always be inverted. All right. So here is kind of coming back to nearsightedness and farsightedness. So I think if you were to remember anything from today, you might want to put that into your memory bank. For nearsightedness, it is corrected with a concave lens, and farsightedness is corrected with a convex lens. We'll spend more time on this in the future. It's in our next section. So it won't be the last time you see this. We'll talk about it in more depth. We'll probably spend a good half a class talking about this again. All right. Again, another video I'll ask that you guys watch. This is another video I'll ask that you guys watch. And then you won't be doing this today, but I thought I'd just spend a little bit of time talking about the SimBucket simulator. You've used this in the previous day when you were dealing with mirrors. So just remember here, it starts on lenses, so you shouldn't have to change anything, but it can toggle between mirrors and lenses. So we want lenses here. Converging lens is the convex lens, and then diverging is the concave. So we spent a lot of time talking today about convex, sorry. You can change the focal points to whatever you want. When you do your investigation in the next day or so here, you don't have to change the focus or the height of the object. It's totally if you want. Now see here that the image is off the screen. If the image is off the screen, you may want to adjust either the focal point, or if the image is off the screen and you like where the focal, you can just adjust where that object is. And so remember, this side here is the object, and this over here is the image. You'll notice here that you can see some weird things happening. So here, you can probably notice already, image is upside down, it is smaller, and it is a real image, all solid lines. You get to 2F point, or the center. This is a unique point as well. It is the same height. Notice it goes up or down one box here, goes up one box here on the grid. So it's the same height. That is what happens when the object is placed at the center point. Okay, it's upside down or inverted, and so it is also a real image. When you bring it inside here, you'll notice that the image is now enlarged. It's still inverted and it's still real. When we get to the focal point, something special happens here. Notice that these rays are now parallel. No image is formed when the object is at the focal point. Bring it inside now, and notice now that these light rays are actually diverging. So when the object is between the focal point and the convex lens, you have to go backwards here to see that it forms a virtual image that is right side up, and it is enlarged in this case. And as you get closer and closer and closer and closer, you can imagine it's going to get to be almost the same shape, or sorry, same size. All right, you could bring it back to the other opposite side, and of course it'll work the same. It's just it'll be going in the opposite direction. All right, and then with diverging lenses, you'll be doing the same thing, and you'll just be asked to look at the different spots. but you'll probably already notice. So if I put it outside here, we got a virtual image. It's right side up and it's smaller. When we get to 2F, it's still smaller, 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 smaller. It's still um, virtual and it's still upright. And in fact, it always stays that way. All right. And of course, if you come to the other side, it's just the exact same thing on the opposite side. So until next time, you guys, stay safe, take care, and I'll see you when I see you.